we're going to look at the vector equation of a straight line. So at this point you should be used to using the equation, a Cartesian equation for a straight line, using y equals mx plus c to find the position of a point on a line. So the idea is similar. We want to write down a vector equation that will tell us the position vector of a point on a line. Okay. So I'm going to draw a line in space, and it's going to be just in 2 dimensions, x and y, and I'm going to put the origin down here somewhere. So that's the point, that's the origin. So to come up with a way of writing down all the points on this line in terms of a position vector, then what I would do is I would first of all find a vector that got me onto the line. So I'll find a vector, and I'm going to call that A. And A is a vector that moves me from the origin to a point on the line. And the next thing I do is I find another vector that points in the direction of the line. I'm going to call this vector D. So I'm going to call that D. So it's a vector of some magnitude, some length, that points in the direction of that line. So let's say I wanted to get to this point here on the line. There. I'm going to call that vector there R. Well, I've tried to draw it so that R is equal to A plus D, which means that this position vector R here is the same as going along this vector A and then along this vector here D, and they're equivalent. Just clear that off. I could also get to another point on the line again, but this point on the line here is going to be A plus 2 lots of D. And I'll show you that to get to that position there, I could travel along A, travel, add on a D, and then add on another D, and I'll get to that position there. In fact, I could get to a scalar multiple. Three would get me about here, and 4 would get me about here, and I could have 2.5, which would be about here. Or I could move in a negative direction down the line by just putting a negative scalar in front of D. So minus 1D would probably get me about there. So in general, move to get to a position on a point on the line, which is essentially what the equation is. Well, the position vector R, which is plus factor, which multiplies the vector D. And then moving along the line in by multiplying the vector d by a scalar. And this here is the vector equation of a straight line, so I'm going to just put a box around that. Now, it's important that you realise the first part of the equation, the a, is just a vector that gets you to the line. Whereas this second part of the equation, the d component, determines what direction the line is taking, which way it's pointing. So if I were to draw another line with a different equation, which was parallel to this line, then the a would be different. It would have a different a vector, but because it's parallel, it would point in the same direction, so it would have the same d vector. So parallel lines would have the same d vector because they point in the same direction. So what we're going to do now is we're going to see if we can find where two lines intersect. So we're going to do a question, and the point is, can we find where two lines intersect? And I'm going to use two line equations in 3 dimensions. So I'm going to say that line 1 has the equation 3, 1, 0 plus t, which is the scalar quantity, multiplying 0, 2, 1. So this 3, 1, 0 is the vector that gets me onto the line, and then I'm going to add a scalar multiple of 0, 2, 1, which is the direction that the line is pointing in. And the second line is going to have the a component 1, 1, 3, and then we've got a scalar multiple, I'm going to call this s, and it's going to multiply the direction vector 1, 1, minus 1. So we want to first see, where do these lines cross? We're trying to find the point where the lines cross. So the point where the lines cross, if you think about what the line equation is, this L1 is a position vector of any point on the line, and L2 is a position vector for any point on the line L2. Okay? So when they intersect, they should be equal to each other. So at the point where they intersect, let me just write this down, where these lines intersect, they can be put equal to each other. So 3, 1, 0 plus t, 0, 2, 1, it's got to be equal to 1, 1, 3 plus s 1, 1 minus 1. Okay, and my job is to basically find the values of s and t that make these line equations equal to each other. So I can just treat each component separately. So the 3, 0, 1 here are all in the x direction. So I will just write down an equation in the x direction, an equation in the y direction, and an equation in the z direction. So that's what I'm going to do now. So in the x direction, I should have 3 plus 0t is equal to 1 plus s. And in the y direction, I should have 1 plus 2t is equal to 1 plus s. Minus s. And so I have 3 simultaneous equations to solve with just 2 unknowns. So you only need two equations to find out the values of S and T, because two equations to find two unknowns. Here we have three equations to find two unknowns. However, we have to make sure that the S and T that we find satisfy all three equations. And that ensures that these lines do actually intersect. They might cross in the X and Y plane, but not in the Z plane. They might be skew lines. So when you find the values of S and T, you've got to make sure that they satisfy all three of these equations. So from the first equation, you should see that we get S. The second equation, that 2t equals 2, so t equals 1. And I'm just going to check that these the values of S and T satisfy all of the equations. So trying S equals 2 and t equals 1 in the first equation, I get 3 plus 0 equals 1 plus 2, which is 3. That's fine. In the second equation, I get 1 plus 2 is 3, and then 1 plus 2 is 3, so that's satisfied. And in the final equation, I get 0 plus 1 is equal to 3 minus 2, and that's fine. So the S and T values that are found satisfy all of the equations. So now all I need to do is substitute the values of S or T back into the original line equations, and they will give me a position vector where the lines intersect. So I'm going to substitute T into L1, the value of T I found for L1, and so I get that L1 is equal to 3, 1, 0 plus, the value of T is 1, so 0 to 1, and that just equals, just by adding these vectors together, 3, 3, 1. So we're suggesting that the coordinate where these lines intersect is 3, 3, 1. I'm just going to check that S works in the second equation, so L2, and I'm going to substitute 2 into this one. So I get 1, 1, 3, and plus 2 times 1, 1 minus 1. And I add these together, so I'm going to get, again, 3, 3, 1. So, finally I can say the lines intersect at 3, 3, 1. Now the second thing I can do is I can also find out where the angle between the two lines. So I've got these two lines, L1 and L2. Oh, kind of a little bit too far. L1 and L2, and I want to know the angle that they make with each other. Now, as we've explained earlier, the first part of the vector, the A part, just gets you onto the line, and the second part, the D part, is the direction of the line. So if I want to know what angle two lines make with each other, the only thing it really depends on is the D part of the line equation, the direction they're pointing in. So what I'm going to do is I'm going to use the dot product to find the angle that the lines make with each other, but I don't have to dot the whole line L1 with the whole of the other line L2. All I'm really concerned with is what direction the lines are pointing in, because that will determine what angle they make with each other. So I don't dot the whole line, don't do the scalar product of the whole line, just the D component, just its directional component. So I'm going to try and find the angle between the two lines, and we remember that the scalar product, A dot B, can be written in two ways. The magnitude of A times the magnitude of B cos theta, where theta is the angle between the two lines. Or I can also work it out by multiplying the x components of the vectors together, and then adding the y components multiplied together, and then the z components multiplied together. So what I'm going to do is I'm going to do the dot product of L1 and L2, just their directional components. So I look back at the L1, and all I'm concerned with in this part of the question is this vector here, and this is the vector for L1 that determines which way it's pointing, its direction. And I'm just going to concern myself with this vector in L2, which is the way this line is pointing, and I'm going to dot these two. I'm going to find the scalar product of these two. So it's 0, 2, 1 dotted with 1, 1 minus 1. So I've got 0, 2, 1 dotted with 1, 1 minus 1. Just check I've done that right. 0, 2, 1 and 1, 1 minus 1. Brilliant. Okay. So I'm going to find out the value of the dot product. So it's going to be 0 times 1, which is 0, plus 2 times 1, which is 2, plus 1 times minus 1, which is minus 1. So we'll get a value of 1. So the dot product is going to have a value of 1. Now, using this equation here that we've written in pink, I can also write the dot product in another way, which is I can find the magnitude of this vector 0, 2, 1, multiply it by the magnitude of the second vector 1, 1 minus 1, and multiply it by cos theta, and we should get the same answer. We should get 1. So what I'm going to do is I'm going to find the magnitude of 0, 2, 1. And to find the magnitude, you remember, it's just going to be 2 squared plus 1 squared, which is root 5. I'm going to find the magnitude of 1, 1 minus 1. Which is going to be 1 squared plus 1 squared plus 1 squared, which is root 3. So now I know that using the pink equation again, root 5, the magnitude of 0, 2, 1, multiplied by root 3, the magnitude of 1, 1 minus 1, multiplied by cos theta, where theta is the angle between the two vectors, should be equal to 1, because I've already worked out the value of the scalar product. So now I have that cos theta is equal to 1 over root 15, and I can find out what theta is. It's the inverse cos function of 1 over root 15. So let's just have a look. I'll put it in the calculator here. We've got inverse cos, let's have a look. Inverse cosine of 1 divided by root 15. There we go, which is 75 degrees. We're going to look now at how to find the perpendicular distance from a point to a line. So I've got here the vector equation for a straight line. It's 258 and plus lambda 102. Okay, so I'm going to try and just draw that line. So the first vector, remember, the 258, is just going to get me onto the line. It's the position that gets me onto the line. So I'm going to go 2 in the x direction, and then I'm going to go 5 in the y direction. So that's sort of 1, 2, 3, 4, Okay. I'm also going to plot a point 2, 1, 3. So let's plot that 2, 1, 3. Well, I'm going to come down 2 again in this direction, 1 up, and then 3 up. So 1, 2, 3. Something about there, I think. Okay. And this point here is going to be point A, and it's got the coordinates 2, 1, 3. Okay. So what we're going to try and do is we want to find a point on the line which is going to be closest to the point A. So I can pick a point somewhere on this line, for example here, P, and I'm going to move P down the line this direction until I get as close as I possibly can get to A. And that is going to be when the line, or the vector A to P, is perpendicular to the line R. So I think, looking at it, point P is going to be about here. Okay, and what we're saying is that when point P is as close as A, close to A as possible, then the vector A to P, and let's draw that on like that. So that's the line for the vector A to P. The vector A to P is going to be perpendicular, so at 90 degrees, to the line R. Okay, that's when they're going to be closest. Okay. So, how do I do that then? Well, first of all, I need to come up with an expression for A to P. But we've already talked about how to do this. A to P, the vector A to P, is the same as O to P minus O to A. So O to P is just going to be the line equation. So P is a point on the line, so O to P is 2, 5, 8 plus lambda, and I'm going to put a little p there. It's the value of lambda at point P, 1, 0, 2. So remember that just by changing the value of lambda, I can get to any point on that line. But we want a particular value of lambda that gives us that point there, P. Okay, and then I'm going to take away O to A. Well, O to A is just its position, the position of A, which is 2, 1, 3. Okay, so I get this expression, which is going to be, let's have a look, 2 plus lambda minus 2. So that's just going to give me lambda P. Okay, and then I've got 5 plus 0 lambda minus 1, so that's just 4. And then I've got 8 plus 2 lambda minus 3, so this is just 5 plus 2 lambda in the bottom. Okay, so that vector A to P is lambda P for 5 plus 2 lambda P. So my job is basically to find out the value of lambda, and as soon as I find out the value of lambda, then I will know O to P, so I'll know the position of P. Okay. So what I do now is I say, well, okay, O to P, this position at P, is going to be the point where the vector A to P is perpendicular to the vector R. And that's going to be when the dot product of the two vectors is 0, because that's when cos theta equals 0. So cos 90 will make the dot product go to 0. So I'm going to do the dot product of A to P dotted with not the line, not the whole line, but just its direction, remember. I'm only concerned with this vector here when I'm doing finding the angle between vectors. The first vector, the 2, 5, 8, is just how to get onto the line. It's this second part that determines direction. So I'm going to dot the vector AP with the vector 1, 0, 2. And I want the angle to be 90 degrees. So I know that the dot product is going to be 0. Okay. So what we're going to do is we're going to dot A to P with 102. So I've already got an expression for A to P. It's lambda P for 5 plus 2 lambda P. And I'm going to dot it with 1, 0, 2. Okay. And so I get lambda P. Plus 4 times 0, which is 0, plus 2 times 5 plus, let's write it like this, 2 times 5 plus 2 lambda P. So that's going to be 5 lambda P plus 10, and that equals 0, because the dot product we want to be 0. So all that it need do now is find out the value of lambda. Well, that means that 5 lambda P is equal to minus 10, and lambda P then is equal to minus 2. Okay, so I've worked out the lambda, the lambda, which is the scalar that I put into the line equation, to give me the point P, which is closest to A. So all I need to do now is substitute the value of lambda that I got into the R equation for the line, and it will give me a position vector, and that position will be point P, the closest point to A. Okay, so let's take that line equation, R, and it's going to be 2, 5, 8. So the position O to P is going to be 2, 5, 8, and the lambda we've worked out is going to be minus 2, and then it's the direction of the line, which was right at there, 1, 0, 2. Okay, and I just add these vectors together, so I'm going to get 2 minus 2, which is 0. I've got 5 minus 0, so that's 5, and then I've got 8 minus 4, which is 4. Okay, so the position of P has the coordinate 0, 5, 4. Okay, and that's the point which is closest to A. So 0, 5, 4.